Hello, I will today I'll continue the Rust presentation. Um, I introduced the meta deposition process in the last time, and in this time I'll introduce epitaxy process and particle channel transistor. First, epitaxy process is depositing one more layer with the identical form of the rust layer. Uh, if the red colored is deposited in one material, and the blue sucker is, suppose the blue sucker is a atom, and if we want to deposit this atom for electrical signal improvement, then we usually use epitaxy growth for identical arrangement. Because if we just deposit another material on another material on the previous material, then the atom arrangement is different, so it can degrade the performance. So it's the reason why we use epitaxy growth. So I heard the extra epichamber in applied extra epichamber equipment in applied materials. There are three technologies there, and they do from pre-cleaning to deposition. Uh, Pre-cleaning mean we deposited the previous layer like this lead atoms. Then I suppose the red atoms are silicon. Then silicon want to bond the oxide in the air. Then even though we don't put the oxidant gas, it is automatically made the SiO2. The combination between silicon and oxide is formed on the silicon atoms. So it is natively made, so it is called native oxide, but it's not for our intent, so it is a defect. So we need to clean this silicon dioxide. Silicon dioxide means the combination between silicon and oxide. Yeah, before epitaxy growth, we need to pre-clean. So there are three technologies in pre-cleaning in applied materials. First one is Cycony, and second one is Clarion, and third one is Ajax. Cycony is previous technology, so I want to say just Clarion and Ajax. Clarion, as I said before, when I suppose the previous layer is a silicon layer, then it makes the silicon dioxide naturally. So we need to remove this silicon dioxide. So Clarion is a technology that remove the native oxide in pre-cleaning stage. And IX is a technology that remove carbon contamination. Carbon exists in the air, so it can be made naturally. So it is a contamination too. So these recent two technology are used in this extra epi chamber. Third, I will introduce particle channel transistor. Usually in planar structure, planar structure. Planar structures channel. Oh, where is it? Planar structure in MOSFET. Yeah, usually planar structure usually planar structure is this. This one is a channel between n-type and n-type, but the channel is line on. So usually channel is with usually channel is with. Oh no. Oh yeah. Usually channel is usually channel is disranked. Usually channel is horizontal direction, but this particular channel is particular direction. I didn't explain it. N-type and N-type is called drain and source, and there are drain and source too. And drain and source form is not same with the planar structure, because originally drain and source is lined up in horizontal direction, but it is lined up in particular directions, and there is a spacer. It is a channel. So channel is not horizontal direction, but particular direction. So particular direction. So it is. So why what so why is it why is the reason why this is called the particle channel transistor. The reason why we use particle channel transistor, we want to scale down the MOSFET size to integrate in a die, in a die more and more in a die more. But if the channel is wrong in the horizontal direction, then it is not good for it is not good for the area. So the solution is particle channel transistor. Particle channel transistor. In our in Korean industry, the memory industry is very developed. So I will say in terms of memory in terms of memory in terms of memory perspective, memory perspective. In DRAM, we need to scale down, and DRAM is composed of 1T 1C. Yeah, it's a DRAM structure. Yeah, it's DRAM structure. The MOSFET is this is a simplified circuit. We usually express MOSFET in this form, and capacitor is expressed in this form. DRAM is composed of gate and capacitor. Capacitor is a device that store charges. So when we think this as a digital signal, digital signal is seen as a binary number, 0 or 1, and computer accept the information as a binary number 0 and 1, and the binary number binary number concept is from this capacitor. When capacitor stores charge a lot, then it is seen as number 1, and if the storage capacitor doesn't store anything, then it is seen as 0. It is seen as 0 number. So when we want to express 32, then we can say just 32, but computer couldn't accept 32 because it is not binary number. So computer can only distinguish binary number 0 or 1. It's the reason why we use binary number in computer. So when we express 32, then we need to express this one to binary number. Then we express like this. I'll change the 8. Binary number is 1000. Then there are 4 DRAMs there. We need 4 DRAMs to express 8. So then there is one transistor. Transistor mean MOSFET or semiconductor. One transistor turn on, then one capacitor store charge. It is the binary number is 1. And we expressed this one, and there are three numbers in 0. So we need to turn off the transistor. Transistor turns off, and one capacitor doesn't store charge. The binary number is 0. So I expressed this zero. Then we need to fill three zeros. So it is so three transistor or three transistor needs to be identical straight. So one transistor turns on and three transistors turns off. So it's the method to express 8 in binary numbers. So this 1T and 1C is a DRAM structure. So DRAM structure. Then we need to put a lot of DRAMs in one chip. A chip is die, so in one chip or one die. Then we need to scale down transistor or capacitor. But we couldn't decrease the area for the high capacitance. Capacitance equation. Yeah, capacitance equation like this. Capacitance is epsilon times. I don't know what is x. Yeah, I'll emit this x and 0. It's just epsilon a over d. So we need to increase a to store high capacitance, because if the capacitance is not high, then even though it turns on, the the computer couldn't accept whether it's 1 or 0, because it is very small. So we need to increase the capacitance. So we need to increase area. So it is impossible to increase area for scaling down. So we are considering to decrease the transistor channel. We are decrease to we are considering to decrease the transistor size. So if the transistor channel is horizontal direction, then it can occupy broaden space. So the transistor channel is built vertically. Then in the process of decreasing transistor channel, the leakage is higher, because as I said before, in the short channel effect, in short channel effect, drain voltage can affect the channel's potential easily. So even though the gate voltage is not high, but channel is opened, so it is called leakage current. When we decrease the transistor's channel, then leakage current occurs. So gate so we need to use hafnium oxide instead of silicon dioxide, and use IgGO for channel, because IgGO has higher band gap. 보자. hafnium oxide. Okay, then MOSFET structure. Yeah, it's a MOSFET structure, and electrode is the gate, and there is a channel between electrode and channel. There is an insulator. When we turn on electrode, when we turn on gate, this electric field reach to the channel through this insulator. But if insulator is relative permittivity is low, then it couldn't appropriately deliver the gate's electric field. So we need to use high relative permittivity material in this for this insulator, but it has trade-off. I don't handle the problem in this presentation. So we want so usually the insulator is silicon dioxide, but we need to use hafnium oxide instead of silicon dioxide. Because hafnium oxide has higher relative permittivity. Yeah, relative permittivity, and we need to use IgZO. This channel is composed of big silicon, because the silicon. But if we use IgZO instead of silicon, IgZO's band gap is higher than silicon, so it prevents leakage current from making. So what that means energy band gap. Yeah. Okay, it is a chart of energy band diagram. Energy band diagram. Yeah. If each energy band gap is high, then it's hard to excite to this conduction band. The flow from valence band to conduction band is current. So when it so the band gap, if the band gap is if the band gap is if the band gap is big, then it behaves as an insulator. It behaves as an insulator property. So IgZO has a higher band gap, so it can be treated as a leader insulator, and it can prevent the leakaging current from making in MOSFET when we decrease the channel effects. And there are other skills in applied materials. When we use CVD process for wire making, we use WF6 precursor, and there is an issue about fluorine, because when we put WF6 gas and we chemically react to this, and we chemically react to this gas, then the purpose is just making W tungsten only, but this F6 is not is not volatile to the air. It remains, so it can be a contamination. So it is, so it's the issue. So but they said but the specialist in Atom said, it's the reason why we use molybdenum for drying. And there is one more technology, HBM, advanced packing. Uh, HBM, advanced packaging. In SK Hynix, the main technology is HBM. HBM mean high bandwidth memory. So it has high bandwidth. So the speed is very fast to calculate to calculate to calculate. So it is conducted to stack up vertically dies, and stacking dies aggravates WAPZ. WAPZ is the phenomenon that vapor is folded because of heating, because there is a concept of thermal conductivity. When thermal conductivity is different, then it can make stress, and it can make stress, and it causes warpage. So there are expansion coefficient and heating problems, but aluminum nitride has higher thermal conductivity, thermal conductivity. So it's good for emitting heat. So it emits heat. So it doesn't expand. So aluminum nitride research is progressed in applied materials. These So I arranged these or ATOM in 2026. Okay, I'll end my presentation.